thanks everyone for coming. This is actually a big thrill for me because I get to share some of my embedded software experience with you guys. And I just wanted to check real quick, how many embedded guys are out here? Embedded software? All right, so this is great. So we have more than I actually expected. So what I did last year when I came is I gave kind of what turned out to be a case study for a little camera system that was built in Erlang using a framework called Nerves that cross-compiles Erlang, or really the C code. The Erlang's the same, not exactly cross-compiled, and made a little camera. So the problem was last year was you could see my project, I could give all these details about it, and I actually open sourced a lot of the pieces, but it was kind of hard to get started on. So I wanted to try to make this a little bit more accessible. And I guess there's just one other note that I wanted to say to all of you who may not be in the embedded industry. The embedded industry is kind of painfully slow at change, so a lot of things that come very naturally to you guys in terms of coding are actually quite new concepts for a lot of the people that I work with. And so don't hesitate to give comments, even if they're completely obvious, because sometimes these things are new. So my route to this project. Well, a couple years ago, I wanted to do something about the C and C++ code that I was writing because I had read a lot about Erlang and I noticed I was reinventing the wheel a lot. And with processors getting faster, especially the ones I used, which happened to be 32-bit Linux processors, a few hundred megahertz. So thinking in terms of a higher level language was not that hard. So I looked at Erlang, and I thought, oh, this looks great. And then I thought, well, has anyone else used it in embedded? And then I saw, oh, well, Ericsson did. The case study for the whole language is pretty much an embedded project. So I said, oh, super. I'm not even taking much risk here by pulling this in a project. So I started looking into Google, so how I get started using Erlang in one of my projects. And I found hits, so I said, OK, good. Let me do a little prototype. And that was last year. And then all of a sudden, I started putting this together, and I noticed missing pieces and other things that just kind of were surprising to a guy that's kind of used to firmware images in the size of tens of megs. So tens of megs for a firmware image is actually huge for an embedded guy. But then I found out that there's another level of huge, and that's that most of the time, most of what I happened to be finding were things that required desktop Linux installs. And then I had fun things like, oh, I saw Megaco and Corvin. I was just like, oh my gosh, I don't quite need all that. And I went through some open source libraries, and it was very clear that there are people doing this stuff. I'm not doing anything new, but it was on and off maintenance. So anyway, so I started up this little project. This was my toy project to try to take to try to build some sort of framework for getting Erlang cross-compiled inside a little embedded Linux system. And my approach, just to make this more interesting, was since Erlang has a lot of the same things that you find in a normal Linux system, let me try to not use the Linux versions that I'm so used to and use the Erlang ones. So and then I'm going to explain this a little bit further for where things ended up. So as I was saying before, I did put some limitations. I'm using embedded Linux. For me, that's kind of a base parameter that I need just to access some device drivers. Device drivers are kind of fun to write, but not fun to write too many. I cross-compile. All the little projects I build tend to be cross-compiled. And cross-compiled can be a pain, but it can also save you a lot of work, because when you develop natively on a device, well, that brings in a lot of baggage. And when you cross-compile, you can just take the pieces that you need. So you actually save some work by cross-compiling. And then I said, OK, fine. Network is kind of a pain, so I'm just going to reuse, call out to the standard Linux tools to set up networks, at least in the beginning and still now. So what are things that you look for in Nerve? So I think these are some of the defining characteristics of the system. So Erlang, well, of course, because what's the point if it weren't Erlang? Minimalist. So a lot of times when you see something in Nerves and you ask your question, is it included or is it not? A lot of times the answer is not. Nerves is very much a minimalist system. that you can be built on. It's like you start small and build, as opposed to a system where you start big and prune it down. And that's somewhat nice. You can build these small systems, and at least for me, I can kind of think that I actually understand a lot of what's going on in the system, which for any kind of big project is certainly a luxury. Now, that's the minimalist. To actually put this together, there's a system called build-root, and build-root is a common, it's a pretty popular project in the embedded world to make the cross-compiler, compile Linux, and build all these Linux tools that you want to include on your embedded system, and then package it up in one root file system. So it's build-root, it's build-root file system. So I reuse this build-root project and customize it in an Erlang to a specific way. The init process for you guys, systemd init or system5 init, systemd, all that stuff. So there's some replication and things that Erlang can do. So I just said, well, I won't think about it. I'll just toss it down, add a little shim. You can't just start Erlang as process one because there are some things that you have to set up in the Linux user land beforehand. But you can have a pretty small init process, and so there's this little project that's basically one C file. It's about that long to set things up and start Erlang, and that's Erlang init, and you'll see that start. Now, when you get to actually using it, how does the Erlang come in? Everything is based on OTP releases, and I guess you don't have to be an OTP release, but it makes things a lot easier. I think that's been a common theme at this conference, to go the OTP release. The last part, I think this is more of an embedded thing for devices that you tend to unplug and replug. A lot of devices that I make, they might stay on for a little while, but it's not quite as important to have these rolling updates like you can do with Erlang. There's nothing against it, those things. It's just I don't use those as much in my work. So nerves, you build an image, they're a big firmware image, and then it's read-only, it's small, and then if you want to upgrade the system, you download the new image, apply it, and since these images are small, it's actually not that big of a deal, and then you reboot to run the second image. So when you start using this, you'll see, oh, why is my whole root file system read-only? Well, it's to support this use case. It actually has a nice side effect that you can yank the power off at any time, and your file system's read-only, so it's a little bit harder to corrupt. Not totally robust against this, but certainly better. So here's what you do when you use nerves. There are two routes for this. So there's the top part, which is kind of the Erlang route, and then there's this bottom part, which is the everything else route. The Erlang route is your standard. You write your OTP applications, you compile them. Now the compiler that you will get for compiling the C code will be the cross compiler, so that you'll actually get ARM binaries if your target's on ARM. And you get down over to Relax to create the Erlang OTP release. Now, in parallel, there's this whole idea about generating a base image. So the base image is a base root file system. And that's really the build root part. So the Linux kernel, Erlang, the Erlang VM, and a bunch of other tools, those will get built and combined into one image. So you have that base firmware image. You can actually boot in and work off it, and I'll show a demo of how that works. But the key thing is that those two paths get combined, and that the output of that is the bytes that you put on an SD card if you're going onto an Raspberry Pi or BeagleBone Black, or if you're working on some other piece of equipment that has soldered-in memory, that's what you copy to that. All right, just a quick note. This cross-compiling thing comes up a whole lot. I just want to say just some small things about it. So this is cross-compile. You program on a host PC, which could be x86. Run the compiler, you get an ARM binary out of it. So that's cross-compile. So there are a couple reasons why you might want to do this, and a lot of them come down to is that you can't develop on the target that you're actually trying to program on. Now that's become less of an issue lately because these embedded devices like Raspberry Pis and the BeagleBones and all that are kind of fast. But how many of you guys have developed on Raspberry Pi BeagleBone that it's kind of fast, but I don't think any of you would say that this is like a happy place if you want quick feedback. So cross-compiling is one place to improve this because your PC is crazy fast in comparison to these devices, even still. And don't feel like you're locked into cross-compiling when you get this. A lot of programs that people write for these embedded devices, a lot of pieces don't actually interact with the hardware directly. There's nothing keeping you from developing that on a PC and then moving over to the cross-compiled environment. A lot of people think that, since I'm using nerves, do I have to program everything, develop everything in this cross-compiled environment? No, you don't. Separate your code in a smart way, and actually that's not even that hard to do. The other thing is if you are doing something really hardware specific and the edit compile debug cycle you feel is too long or if you're less comfortable with it, just install like Raspbian on here and do that piece. All right, so let's get to building something. So this first part is, well, what happens when you decide that you want to use or want to try out Nerve? So what does that look like? So this is the first part is that you have to clone Nerve from GitHub. And I'm not going to do that because it takes a little bit, but this part I had like the choose your own adventure thing because Nerve supports a couple varieties out of the box, which if you like to program in Erlang or Elixir or LFE, and I got to think, I'll let you guys choose, but then I realized that one of those languages actually had cross-compiling going on. That's LFE. So I'm going to go with that one because it will be slightly more interesting. The other shells don't have that much, they don't have code specific to the shell that's C or C++. So let's just imagine that we get cloned nerves and we just put it in this directory. So the very first thing that you want to do when you get nerves is you have to provide it a configuration. And there are a lot of configurations that you might want to start out with. So you can see them, and hopefully this will show up. So I would say these bottom ones, these are starter configurations, and the README has a little bit more information on what they do. But essentially, they'll get you an image that's going to boot for one of these boards. BeagleBone Black, Raspberry Pi, AG150 and Elix, those are x86 boards. If you're not using one of those, you're not lost. You can go to the build root project, and they have several ones. And then if you look at the build root project, you'll see that what I did is a fairly straightforward extension. So we're going for this. We're going to go to the nerves RPI LFE. So we'll do that one. So that's all it does. So you say that make that def config, and then all of a sudden in your build root directory, you'll have this file called .config. And this is a build root thing, but it will save it for you for the next time. Now, the next part that you do is you type make. And make is going to download the Linux kernel, your cross-compiled toolchain, all this stuff. But before we do that, I wanted to show you something. So this is the latest and greatest GUI technology to let you pick what you want to have on your target. So the base image is cool, but like I said, it's minimalist. So as you start programming, just using nerves, just remember if you want to get something, just go back to your base image, and you can add C code or modules that I may not have included. So the two places you're going to go are probably target packages, and I'll just give you there's like tons. So anyone who's done apt-get install, there's like a billion packages. Well, build root is kind of the same thing. Your billion packages are in this menu, and you can use the / key to search for them. But basically, all you have to do is go over and say, oh, I want a Vahi, which is for 0conf, and you just say yes. And the next time you build the base image, that will be, the Avahi program is going to be in user bin, and you can call that from Erlang if you want to use it. But, so let's go back here. The other place in build root that you'll want to see is the nerves options. So the nerves options, since nerves uses build root, it ends up in this user provided options directory. And now these are things like we want Erl init. Of course, we want Erl init, so that's how we start Erlang. There are a couple other things. LFE, we happen to pick that config. Now, down here, there's this thing called nerves config. And this is to give the base image just something that boots and is configured somewhat rationally. I look at it as a way of selecting through the menu of certain options that are going to go in the vm.args. So when the VM starts, you can pass some arguments to it, like the sname, cookie, stuff like that. A simple way to get started. When you actually develop with this, you're not going to use this. You're going to you might copy the files that it creates as starting templates for your stuff, but then you'll get past it. Sorry, let's not say that. Okay, so the next step is to run make, and so when you do this at home, just leave your computer on. It'll be about 20 minutes later if you have a pretty fast computer, maybe a little bit longer. But at the end, what you're going to get are two images here. And let me actually just show this a little bit better. So the build-root output images, there are two files in here. One's that .fw file, and the other one's the .img. So the .img I'll start with. So the .img is the file that you can copy byte for byte onto an SD card. So SD cards, there's nothing magical. It's like one big byte array. And the image file is basically that byte array for the beginning. You could use a tool like DD to copy it onto there. This other file, the .fw file, is a zip file, which has the root file system and Linux kernel and whatnot, all the pieces inside of it. When you actually get to using nerves, the .fw file would be a piece that you could distribute to someone to upgrade their system. So for this demo, let me just plug this in. And let's see. So hopefully it will come up. All right, let's see. I didn't see the message, so it might not have come up. I might have a little makefile target to burn it. So we'll see. It'll see whether the thing's in there. So the first step when you have the SD card is just to burn a complete image onto it. You can make upgrades from that, but it doesn't make sense to upgrade something that doesn't have an image on it already. All right. Let me try again. Good. All right, so the nice thing is that on my system, it auto mounts. That can also be a little tricky because you can't write low level to an SD card that's mounted. Well, you can, just things can get corrupted. The firmware update utility will automatically unmount it for you. So this thing's going to copy. So then the next step, when this thing's done copying to the card, so this is the first time copy, so it will take a little long. But what we're going to do is plug it into this Raspberry Pi. So this is a Raspberry Pi Model B, and this cabling looks kind of crazy. Normally I have my Raspberry Pi in a little container, and the GPIOs, all the little pins on the Pi that you can connect to hardware, I have coming out through a ribbon cable. And this goes to a little board that just goes to a serial port. So you guys are familiar with serial ports, right? It's a very common way of interacting with embedded systems. So let's see, that's done. So let's just get this in here. And all right. And hopefully this will work. All right, I'll plug it in, and all right. So this is what's coming out the serial port. And then, okay, so it booted, and LFE's there, and we can do, we can do Lisp. So that's a base image. So I mean, you really can't do too much with the base image. But the idea is that we'll eventually pull in apps, your own apps that will actually do something more than just add. Now, just a couple notes. So I won't show this, but Erlang distribution works fine. You can actually set this up, connect to a network, and start pushing code over it, over the net, and communicating. The default nerves builds come up, and the host name of this device, which you can is by default nerves hyphen, and then 8936. So all the Raspberry Pis have a unique number. So it just has 4 of those bytes so that you can actually have multiple of these out of the box on your network. All right. So, oops. So okay, that's good. But now we actually want to do something which I have learned something that now that people kind of like to do robots. So let's start putting this together so we can actually build a robot. So for this, what I did was I took a robot that I built for my kids to program, and then to make it a little bit more impressive here, instead of putting the Arduino on, I put a Raspberry Pi. And so it has a Raspberry Pi on it, and then wrote the code in Erlang. But how you get started building this frame. So this frame is actually a very popular frame for building hobbyist robots. This is called the SumoBot frame. The Node.js community started something called NodeBots, where they go to conference and actually build frames like this, except without the camera and without the Raspberry Pi. They do it with Arduinos, and then controlled from their PC. But they publish the plans to make these. So these are laser cut plans. If you can find a laser cutter, and if you have a local makerspace, they probably have one. So these things are like hardware, like shop for programmers. Seriously, it actually makes shop class, would have made it a lot more fun. So the laser will cut it out, it'll be perfect, and then you can just assemble it. So that's that piece. So let's get back to the software. Now, the next part, the important part with software, and especially with Erlang, is how are you going to control things? And I'm giving these next couple things are in general for these open source projects that are available. I know from searching Google that there are many others. These are the ones that I have used. So Erlang AL, the AL projects, which you may recognize, they've actually been presented in the past here. Those are for interfaces like GPIO, I2C, and SPI. Those of you who are not familiar with hardware, once you look for a little device, those acronyms are going to pop up all over the place. So just to remember to match those. There's another package called Erlang Serial. So if you want to communicate over a serial port, and so this would be, for example, GPS chips tend to like to communicate via serial, but there's also many other things that like to communicate via serial. So that's a package called Erlang Serial. There are many forks of this package, and I think this one certainly works. I think this is a good one. So that's where to look. So all right, getting back to the robot. Now, I just want to explain, so we're doing this in the context of what's basically a toy robot, but a lot of these concepts transfer to industry. So even though I'm explaining something that is kind of silly and fun, I mean, a lot of this stuff is very similar, although albeit on a bigger scale. So this robot uses servos for the motors. And servos, the way they normally work is you tell them, tell the servo which angle you want to go to. You want to go to 45 degrees, it goes 45 degrees, 90. So someone figured out that if they removed a sensor inside the servo, they just make it a motor and sell it. And they actually sell a ton of these. They're really messed up servos, but that's okay. Having a geared down motor in a standard package is very convenient in the hobbyist field. So these mount very easily on there. And then you can concentrate on controlling them. And so the way they're controlled is you send pulses to them. So it's very simple. There are 3 wires. 2 are for power, 1's the signal. And that signal wire, you send pulses. And each pulse is about 20 milliseconds apart. It doesn't need to be perfect. The duration of that pulse is what's key. And that duration of the pulse is measured by the servo, and it determines whether the servo goes one way or the other way. And that's, if you have it at 1.5 milliseconds, it stays in the neutral position. And then if you go up to 2 milliseconds, it goes one direction. Down to 1 millisecond goes the other. That's the general idea. This is a hard real-time thing. This 1.5 milliseconds, you have to be within microseconds, or otherwise the servo's going and it's no good. You'll see. So I'm gonna go in a little bit about how you control this, because I think that for non-hardware people, there's some confusion possibly here on control strategies for some of this hardware that will make your life harder than it should be. So an obvious strategy for this, so you make these pulses. So why don't I just say GPIO? GPIO is just, you can turn the wire on and off. So let's just turn the wire on, sleep a little bit, turn the wire off, sleep a little bit more, and repeat. So you can imagine this. Well, this is called software PWM, and doing it in Erlang, well, there's so many problems. This timer sleep's not going to give you sub-millisecond accuracy anyway, so that's going to be done. But there are tons of context switches. It just won't work. Some people do it in the C language and do a little bit better job of it. But when you're running on a Linux system, at least when you get to devices that have to make some more guarantees about how reliable they are, Linux has, well, it's optimized for throughput. And while it has real-time extensions, you find yourself going through all this complexity. So software PWM is something that I shy away from, even though I know a lot of people have libraries in this, but it's safe. Erlang's not going to come close, especially with these microprocessors, to doing this. The next approach, which is nice to take, is to use hardware PWM. So turning a wire up and down, well, that's so crazy simple. Even a hardware guy could do this and put it on the chip. So they can do this and put it on the chip, but then they only put 1 or 2. And it's kind of like, well, I kind of need more than that. And then just to make matters worse, how that turning on that wire on and off is different all the time on all the boards. So you have to have a Linux kernel driver, which even though they have this generic framework for doing it, well, the Raspberry Pi, the mainstream people using the Raspberry Pi don't use it, but it's kind of a frustrating mess. So I didn't do that. So here's the approach that I tend to take for a lot of these hard real time. This is simplistic on this one, but it scales to others, and that's just use a microcontroller. So it's C programming, but it's really easy. So compared to what you guys do in Erlang, this is like pretty easy stuff to program these microcontrollers. And some of these chips, like on the BeagleBone Black, they have the microcontroller built into the main chip, so you actually don't need to buy one. But Raspberry Pi didn't have one, so I had to buy one. So I spent money on the AT-Tiny 85, which you may have heard of, the Atmega, which is used on the Arduinos. So there's no professional embedded software engineer. I'm not sad about using the Arduino IDE, and neither should you, to do this stuff, because it really does make this stuff easy for the problem it's trying to solve. Okay, so I use these chips. You guys probably can't see it on here, but it's connected to the Raspberry Pi over a bus called I2C, and I'm going to show you guys how that works. And then on the other side, it's connected to the servos. So here's a picture showing the connections of on this spot. So there's a little purple board on this top. So you can make PCBs for $3. This is a $3 PCB, so it's just connecting wires effectively, according to this schematic. So the robots are battery powered. For AA batteries, you need to have good power to the Raspberry Pi. So what you do is you just buy one. If you go to like Pololu, they'll sell you little regulators for whatever voltage you want, and it will. If the battery's discharged, it'll bump the voltage up to 5 volts for the Pi. If you happen to have a good charge in your batteries and you get over 5 volts, it'll bump it down. So that's going through the Raspberry Pi. The Raspberry Pi Model A right there, it's communicating via I2C to the ATtiny85, and then the control signals are being sent to the servos. I also added, since I had a microcontroller, I can check battery level. So checking battery level is just a matter of using what's called an ADC, analog to digital converter. So all it does is you can ask that pin how many volts are on it. So that's what I did. I figured that might actually come in handy if my batteries are getting low. So I put it on there. And that's also another thing that, for many reasons, processors like the Raspberry Pi don't have ADCs on them. So you would have to go to an external chip anyway. All right, so let's talk about the I2C. So this is sending messages back and forth to hardware. And this actually maps surprisingly well. And I'm going to give a little demo for how this maps into Erlang. So what you do on I2C is it's a bus architecture. And you can have multiple chips on it. Each chip has its own address. So I have to pick an address, because that's what you do. So I picked address 4. There's nothing magical about 4. I just picked it. The protocol for communicating over that is implemented per chip, but there are conventions. And when you start using these chips, they'll get familiar to you. But basically, it turns out that you read and write registers. So the chip exposes basically a block of what looks like memory addresses, and they just call each index, each byte offset a register. And you can read or write them, and what you do is, the first thing you do is you write a number, and the destination chip will say, okay, that first byte that you wrote, that's going to be the register I'm going to start at. So say you say I write 2, and then the next bytes that you read or write will read or write from the second register and then auto increment. So that's okay, good. So then let's just show this. Oops, all right. So here, this is going to be. What I'm going to do is make the NERVs project that can read and write this servo. And so I'm going to do this in Elixir because I'm going to use Elixir AL. And it also so happens that Elixir makes some things surprisingly easy for me to do live. So as with every Elixir project, what you do is you do mix new, and then let's just mix new that. So I'm in here, have my project, and what I'll do. What I want to do is I want to add the mix file to the mix file my dependency. So I have 2 here. The first one is XRM. So I want to make a release, right? So the way with Elixir to make releases, there's a tool called XRM, which is amazingly convenient. So we'll just add that to the dependencies, and let's see. Let me just get that. And then the other library that I want is Elixir AL. So let me add that to the dependencies. Okay, so I have that part. And then let me just, so to get Elixir AL into the application, I'll have to put it up here. All right, did that. now I'm going to do another thing. So this is the mix new gives you kind of a stub of an application. So to make this slightly less non-trivial, I'm going to start the I2C process from the supervisor. So the I2C process is what's going to do handle all the communication to and from that AT-tiny. And let's see, the way that we do that is, so I'm opening up this, and hopefully for the Erlang guys out there who maybe haven't seen Elixir, will kind of see some familiarities here with the application and starting up the supervisor, and then I'm just going to add a worker here. Now, for Elixir AL, that's going to be the I2C, and then it's going to take a couple parameters. The first parameter is which I2C bus that you want to use. You look up the documentation. Raspberry Pi says use I2C-1, and that's what we use. Next parameter is what's the address of the device. So that's 4, and because I'm used to seeing these addresses in hex, I just put them in hex. And then let's just register that, just so I can get to it in the shell. Okay. And then the last thing that I'll do is I have a makefile helper to try to make this easier. And so forgot to do this. There's one important thing when you cross-compile and all this stuff is you have to have your environment set up right. So let's oops. All right, so then I'm just typing my make. Make is just going to do get the dependencies and build it. There's actually a big hex win. Hex is the package manager. So I don't know if you guys noticed this. I'm not connected to the network, and it got my packages and built it. It turned out it was in cache, and this blew me away the first time I built without any network access. I just had assumed it was always going to the network. So we built the app. It's going to start the I2C, so I'm going to put in an SD card. Okay. And the good news about this SD card is I've already programmed it, so I can do the upgrade. All right, so it upgraded it. Now let's go over to, let's try this one. So we'll plug this in. And actually, since we're not dealing with the camera for this part, I don't need to have that on. But I will connect the serial cable so you can see what happens. Let's power up. Okay. So it's powering up. And all right, so same thing, except we're in Elixir now. And so now just the API for reading from I2C, just to send the message to get some bytes. You just type I2C to read, and then let's see, we're going to do bot to I2C, and let's get 6 bytes. And it got 6 bytes. So this is possibly a little hard to read, but the first 2 bytes, the left servo's duration, that pulse duration in microseconds. And actually, let me just see. actually, I'll just skip this. So, so we can keep on doing this and keep on reading this, but you'll notice one thing, I didn't write to see which register I was going to hit, so I'm reading these bytes, and it kind of doesn't make that much sense. So, or it doesn't make much sense because the registers, that you keep on getting different registers. This is like a common mistake. Yes. So the trick here, that's it, right? Let's see, is just to use another function just to write first and then read, and this is very common. Oops, wow. Oh, we actually had a blip there. This is a very common thing, just to write the register, to read the 6 back, and you'll see that you get those back. So the last thing I want to do just before I show the bots actually running is just to actually show that you can write them. So the first step is, let's just say that we want to turn the left motor, and then let's do this direction, and we want to I switch between Erlang and Elixir, and I always forget the bit syntax. So what all this is saying is write 1200, so 1200 microseconds to turn the wheel, so that's going to turn it one way. And it's little Indian. I2C is always little Indian for some reason, or almost always little Indian, and 16 bits. And I don't know if you can see it, but start turning. And let me just stop it. So that's the basic idea. So you can simply turn the wheel. So I'm going to quickly skip to the rest of the pieces, because those were the important ones that I wanted to show you guys, because if you can turn a wheel, you can actually get really far. So I mean, the next step is really just turning the second wheel, almost. And then it's all stuff that you guys are very used to. So the next part of this is to control it via the web. So I just used the Cowboy sample app almost directly to have a little WebSocket control it, which way the wheels turn. And then I reused last year's. Last year's I gave a presentation on setting up video, and video on these is motion JPEG, streaming the frames. Turns out that there's this multi-part bind trick that you can do with browsers to make things really simple. It's totally not scalable to anything outside the LAN, but it works inside the LAN just fine. So let me just get this other guy going. Oops. Oh, shoot. Well, it could be this one. I'd have to look to see which one I just hooked up. Let's try that other one, see if we boot. All right. Well, one thing I can do while this guy boots, or I forgot what his number is, I can try to answer any questions, because I know we're probably getting close on time, right? Okay, so
there's a coffee break
yep.
right now, so I guess we can go into it a couple of minutes.
Yes, actually, I know it's wrong. The one thing that I forgot to do when I had trouble. Ethernet always helps And also, let me just make sure I get the right one. Yay! Okay, good. All right. So that one's this guy, and I can drive him around carefully. So, oh, so all right. I will not drive first person on the table, but you can kind of. So there you go. So that's turning a wheel, 2 wheels, and then connecting it. All right, so I guess we're out of time, but I'll be around here if you guys have any questions. Oh, sure.
I was going to say, presumably if Erlang is doing anything, your battery life is going to suffer.
You know,
So is that idle stuff going on?
you know what? Erlang is totally in the noise. I mean, it's kind of amazing. There are a lot of other things. The stuff that takes power on this, so the motors take tons.
I mean, when the robot's off.
When the robot's off, if you're just running this Raspberry Pi Model A, when I've measured it, it's taking about 100 milliamps. If Erlang's cranking, which cranking for me maybe shot up like 10%, 20%. So so that's 100 milliamps. The motors will bump it up to 300 or 400 milliamps, and the Wi-Fi another couple hundred. So my view on Erlang for this is it's in the noise compared to the other pieces. Anything else? Okay.
So I had a question on how you're utilizing Erlang or Elixir.
Yes.
So one of the things that, as your demo even showed that, the sensors every now and then will fail.
Yes.
So it does require some robustness.
Yes.
How is Erlang or Elixir able
So
to help there?
this is a really great question. So how does Erlang and Elixir help? And I have an example from last year. So last year I built this camera, and basically it streamed. Basically it was the same as this one. So it worked flawlessly when I demoed it, and I thought. And then I went and looked at it, and the C port had actually crashed and restarted, and I didn't know it. So that was that was a huge win. I mean, a lot of this hardware stuff sometimes goes bad every once in a while. I mean, we try to engineer this so it doesn't go bad nearly that, so that would last a little bit longer than that.
But do you have a specific recovery mechanism? I'm just wondering what you're pointing out. Restart seems to be a different, not a particular recovery.
Restart of the individual components is pretty good for most of this stuff. When stuff fails a little bit more often, there's usually an electrical issue that's behind it,
Yep.
and those can be resolved through some work, or worked around with some robustness to the communications protocol.
Okay.
All right.
That's all the time we have. Thanks again.
All right. Thanks.